Here we have the basic algebra-based first-year physics class. This is topic 4, forces, otherwise known as dynamics. This is section 4.5b. You probably already watched section 4.5a. In section 4.5a, we covered the universal law of gravitation, the universal gravitational constant, and how to calculate gravitational forces between two objects. In this, section 405b, we'll be talking again about the big G equation using the universal law of gravitation, and we'll be covering sections 4, 5, and 6. Number 4, how to calculate acceleration due to gravity for any celestial body. Number 5, how to calculate the weight of an object on any celestial body. And finally, number 6, basic kinematics. Remember back to September, dropping things, throwing things, etc., etc. Basic kinematics on other planets, moons, other celestial bodies, all right, etc. So again, this is the second video of a two-video combination, which makes one big video. All right, 405A and 405B. All right, in 405A, we cover the first 3. 405B, we cover 4, 5, and 6. So now, continuing from the previous video, 4.5a, we're going to be deriving the equation for acceleration due to gravity, g, so we can figure out, calculate the acceleration due to gravity for any celestial body. Now, looking here, you'll recall that this is a simple equation to find the weight of an object, all right, and this is the more complicated version of that equation to find the weight of an object. Now, what we're going to do is combine these two equations to derive an equation for G, the acceleration due to gravity on any celestial body. Now, what I'm going to do first is I'm going to reverse the G and the M, because it doesn't really matter. All right, mg or gm, all right, mathematically that's the same. All right, so I'm going to put G here and M here, and then I'm going to discuss the fact that if you put the mass of an object here and multiply that by the acceleration due to gravity of a celestial body, you will get the weight of that object on this celestial body. Now, I'm going to call this M2, because what I'd like to do is I'd like to take an object, all right, like a box, and I would like to rest that object on the surface of a planet, like, for example, the Earth. And I would like to, for this video, I would like to call the mass of the celestial body M1, and I would like to call the mass of the object M2. And again, this doesn't really matter, but for clarity in this lesson, I'm going to stick to that, where M1 will always be the mass of the celestial body, and M2 will always be the mass of the object, whose weight we'd like to know. Now, what you see when you switch, what you see very easily when you switch the M and the G, as we've done here, is that the two F's line up and the two M2's line up. And so what that means mathematically is that this G is equivalent to big G M1 over R squared, where M1 is the mass of a certain planet, R is the radius of that planet, because technically R would be the distance between the centers of the two objects. But when you're talking about a distance that extends from an object to the center of a planet, for the Earth, for example, if the radius of the Earth, that's here to here, if the radius of the Earth is approximately 6 million meters, approximately, and the box, let's say the box is 1 meter tall, then from here to here, from the bottom of the box to the center of the box is, let's say, 0.5 meter, you're not going to add these two together and come up with 6 million meters. All right, that 0.5 is just not big enough to be significant when the radius of the Earth is 6 million meters. All right, so again, this is the mass of the celestial body. This is the radius of the celestial body. G is the universal gravitational constant, and what you will get is the acceleration due to gravity on the planet whose mass and radius you have plugged in. All right, so let's put this equation over there because we've now managed to derive the equation for G. All right, so what you find is that G, little g, the acceleration due to gravity for any celestial body, that would be a star, a planet, a moon, all right, an asteroid, a comet, whatever, all right, is going to be big G, all right, m over r squared, where m and r pertain to a specific celestial body, and g is the acceleration due to gravity for that celestial body. Okay, so now what I'm going to do is we're going to calculate G for several common celestial bodies in our solar system. So what we're going to do here is calculate the acceleration due to gravity for the Earth, for the Moon, and for Jupiter. Now, here's the equation. G equals gm over r squared. Now, we're going to need the mass of the Earth, all right, hence all of these subscripts. All right, the mass of the Earth, the radius of the Earth, we're going to get the acceleration due to gravity for the Earth. Here, with the mass of the Moon, the radius of the Moon, we will derive the acceleration due to gravity for the Moon. All right, take a look at all of the subscripts. When you've got several different M's and several different R's and several different little g's all on the same page in the same problem, you really have to start using appropriate subscripts. All right, now I just picked E for Earth, M for Moon, and J for Jupiter. Okay, the mass of Jupiter, the radius of Jupiter, and the acceleration due to gravity of Jupiter is what we will be calculating. Now, I tried to go online and find all of these numbers to at least 4 significant figures, because I would like for my answers to be significant to at least 3 significant figures. You're going to find quite a bit of variability online. I mean, obviously, Jupiter is a gas giant. If they're going to measure the radius of Jupiter, where are they stopping? I don't know. We look it up, okay? But in any case, we've got big G to 4 significant figures, 6.674 times 10 to the negative 11. We've got the mass of the Earth to 4 significant figures and the radius of the Earth to 4 significant figures. Now, what I've done here is estimated, all right, we tend to approximate the acceleration due to gravity for Earth to 3 significant figures at 9.81. We'll see how close we get to 9.81. The Moon, I've seen the acceleration due to gravity of the Moon as 1.62 or commonly 1.64. People will commonly say that the Moon's acceleration due to gravity is approximately 1/6 that of the Earth. And what you find, where's my calculator? Okay, what you find is that if you take this number, all right, 9.81, and divide it by 6, all right, you get 1.635. So you commonly see the acceleration due to gravity of the Moon rounded to 3 significant figures as 1.64. All right, but you will note in the little chart that appears on the worksheet or on many charts that you see online that the Moon is listed as 1.62. All right, whatever, big deal. We don't really care. 1.62, 1.63, 1.64. First year physics, we really don't care. We're not firing anything. We're not trying to land a rocket on Mars, okay? So we don't need, 5, 6, 7 significant figures, or however many significant figures they're using to do that, to be that accurate. All All right, and for Jupiter, I've seen 25.95 quite often. I've seen 25.90. All right, so these are the estimates that are usually seen on the internet and in textbooks. All right, so now what we're going to do, very simply, all right, is calculate. All right, I'm going to do all this math, put the answer here to 3 significant figures. All this math, put the answer here to 3. Maybe I'll write down 4 significant figures, and then we'll round it off to 3 significant figures. All right, so here we go. Okay, 6.674. All right, exponent negative 11 times 5.972. Exponent 24. I'm going to hit equals. That's the top. Now I'm going to hit divided by. I'm going to open the parentheses. 6.371. Exponent 6. Raise that to the second power. Close the parentheses. And I'm getting 9.819. All right. I'm getting 9.819. All right. Meters per second squared. So really, this would round to 3 significant figures. I'm getting 9.82. All right, and I went through all these numbers a couple of times trying to find, how could I get that closer to the 9.81 that we all know and love, and I wasn't finding a solution to that. So this is the best we're going to do. All right, and not a problem. All right, now here. All right, here we go. 6.674. Exponent negative 11 times 7.346. Exponent 22. I'm going to hit equals. That's the top. I'm going to divide that by, open the parentheses, 1.737. Exponent to the 6th. Raise that to the second power. Close the parentheses. I'm getting 1.624. 1.624 meters per second squared. So finally, let's calculate the acceleration due to gravity for Jupiter. All right, we've got 6.674 exponent negative 11 times 1.898 exponent 27. I'm going to hit the equal sign. That's the top. Divide that by, open the parentheses, 6.991 second to the 7th power. Raise that to the second, square it, close the parentheses, 25.918. All right, 25.918 meters per second squared is what we're getting. All right, so if we do this to 3 significant figures, here we've got 9.82. Here we've got 1.62. And here we've got 25.92 is what we're getting. Well, actually, all right, we'll do this to 4 significant figures. All right. All right. So, we are getting the conventional accelerations due to gravity to 2 significant figures. We're matching 9.8 to 9.8, 1.6 to 1.6. All right, the 2 is a little bit of a discrepancy. Often you'll see 1.64 in the internet. And here, 25.9, not really to 3 significant figures, to 2 significant figures. To 2 significant figures, it would be 26 and 26. So, we're matching the acceleration due to gravity that you commonly find on the internet to 2 significant figures. That's about the best we're going to do. All right? Now, what we're going to do next is calculate weights of objects, all right, using both equations, Fg equals m times g, and the law of universal gravitation, Fg equals g, m1, m2 over r squared. All right, so now let's calculate the weight of a 7.5 kilogram bowling ball resting on the surface of the Earth using the the easy equation and the slightly more difficult equation. Now we should get approximately the same weight using either equation. All right, let's see if we get approximately the same weight. All right, so we've got the mass of the bowling ball, 7.500 kilograms. All right, we've got G for the Earth. We'll use 9.81 meters per second squared. All right, here we've got big G, again to 4 significant figures. All right, 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. We've got the mass of the Earth, all right, 5.972 times 10 to the 24th kilograms. All right, I'd love to be able to multiply the 7.5 in the same line, but it's not going to fit, so we're going to squeeze it in there and say, okay, all that's up on top, getting multiplied. All right, and on the bottom, we've got the radius of the Earth, 6.371 times 10 to the 6th meters. That whole thing gets squared. Okay, so let's do this math and see if we get the same weight for the bowling ball using both equations for weight. Okay, so here we've got 7.5 times 9.81. We're getting 73.57, all right, newtons. All right, so Fg is 73.57 newtons. Now, earlier we found that we were getting about 2 significant figures. So let's just say 74 newtons. All right, and see if this one gets us at least the same 2 significant figures. All right, that seems to be the best that we're getting here with the numbers that I was able to find on the internet. Negative 11 times 5.972 to the 24th times 7.5. All right, now divide that by, open the parentheses, 6.371 times 10 to the 6th. Square that, close the parentheses. Aha! We're getting 73.64 newtons. So again, to 2 significant figures, we agree. All right, so this equation and this equation are basically the same equation, and you get basically the same answer to 2 significant figures. Now, if we could be a little more accurate with some of these variables here, we would get 3 significant figures or 4 significant figures in agreement. But this isn't bad for our first year of physics. Again, if we were trying to land on Mars or the moon, I'm not sure how many significant figures we would need. That's an interesting question. I think I should do a little research about that, or maybe you should do a little research about that. How many significant figures does it take in these kind of calculations to land safely on the moon or Mars and maybe come back again, with some samples, or bring the guys back or the girls back? All right. I'd like to show you an important math trick, especially for those of you who are thinking to go on in engineering and the technical sciences. All right. Sample problem 4.5.6. A crate weighs 29.43 newtons on Earth. Calculate its weight on Mars. All right. Now, what you could do, of course, since you know that the acceleration due to gravity on Earth is 9.81, what you could do is figure out the mass of the object. All right. So the weight on Earth is equal to the mass times the acceleration due to gravity on Earth. All right, so if I solve this for m, you find that the mass of the object is equal to the weight divided by the acceleration due to gravity. All right, so if we take 29.43 newtons and divide it by 9.81 meters per second squared, all right, 29.43 divided by 9.81, we find that the mass of this object, this crate, is 3 kilograms. Now, of course, you know that the mass stays the same when you move the object to Mars or the Moon or Jupiter or float it in outer space or whatever. So the mass can go here, all right? Now that we know that the mass of the object is 3 kilograms, the mass can go here, all right, 3 kilograms. All right, we look up the acceleration due to gravity on Mars, 3.77 meters per second squared, 3.77 meters per second squared, and we get that the weight of the object on Mars, well, obviously it's going to be less because the acceleration due to gravity for Mars is less than for Earth. So 3 times 3.77, okay, 11.31. So 11.31 newtons, all right, is the weight of this crate on Mars. All right, now, there's nothing wrong with doing it that way, all right, solving for the mass first, all right, and then plugging it into the standard equation for weight, given that we know the acceleration due to gravity on Mars. But there's a much more elegant way to solve this problem mathematically. And this will be useful, again, for those of you going on to AP Physics, going on to engineering, going on to medical school, etc., etc. All right, or people who just want to be, real good at math. All right, which is useful in hundreds of different fields. All right. So what you want to do is you want to say, you've got 2 separate situations here. You've got the calculations for Earth and the calculations for Mars. What you want to say to yourself when you've got 2 different situations, you want to say, what is equal in both situations? Well, it's the mass. We know it's the mass that's equal in both situations. And what you do is take everything that's equal and put it all on the left side. So I'm going to solve for mass and get the mass on the left side. I'm going to divide by GE, and I'm going to find that the mass is equal to FGE divided by GE. All right, over here, the mass is equal to FG on Mars divided by G on Mars. Now, since this mass is equal to that mass, that means I can set this equal to this. All right, so I'm going to erase all this, and we're going to say this equals this. And what we've effectively done is eliminated the m. We don't know m anyway. We did solve for m, but initially we did not know m anyway. So it's nice that we can get the m to disappear. We don't know how much it is anyway. All right, because the m is the same in both situations, we can get the m to disappear. All right, so I'm going to put FGE over GE equals FGM over GM. All right, and then we're going to start plugging into that equation. All right, it's really a ratio. All right, so FGE over GE is equal to FGM over GM. Okay, now we can start plugging in because we know 3 of these things. The one thing that we don't know is FGM. All right. Now, we could solve for FGM. We could. I'm just going to start plugging in, and we'll solve, we'll cross multiply later. All right, because this is a nice ratio. All right. What I'm saying is you could cross multiply now All right, and you would get that FGM is equal to, all right, that times that, divide by that. All right, so it would be equal to FGE times GM over, right, GE. All right, so you could plug in here or you could plug in there. Either way, you're going to get FGM. All right, so let's plug in. Like I said, this is a nice ratio. All right, I tend to get very anal about this, and I want to solve for exactly what I'm looking for, which is this one. But this is such a nice ratio. We'll use this version of the equation. All right, the weight on Earth, and you really want to say out loud to yourself what it is that you're plugging in so that you don't make mistakes. All right, the weight on Earth, 29.43 newtons. All right, now let me erase this because we're going to need this space. All right, divided by the acceleration due to gravity on Earth, we know that's 9.81 meters per second squared, equals the weight on Mars, all right, which we do not know yet, divided by the acceleration due to gravity on Mars, 3.77 meters per second squared. So we're going to cross multiply, all right, multiply this times this, divide by that, and we're going to get our answer, right? So 29.43 times 3.77 equals, all right, and then divided by 9.81 equals 11.31, just like we got when we did it the other way. All right, so the weight on Mars is 11.31 newtons. And we've got three significant figures. So to three significant figures, the answer is going to be 11.3 newtons. All right, so again, the steps, to be elegant with our math, the steps were like this. We knew that we had two separate situations that had something in common. The mass was the same in both situations. The weight on Earth versus the weight on Mars. We took everything that was equal and put it all on the left side. In this case, the only variable that was equal was the mass. So we put the mass on the left side for the first equation, for the second equation. Once we did that, we were able to set the two equations equal to each other, and the mass dropped out. The mass, which we didn't know anyway, disappeared. And we're very happy about that because we didn't know the mass anyway. Once the mass disappears, then we're left with things that we know, and we can plug in and solve for what we're trying to find. All right? The key is figuring out what's the same for the two situations and putting that variable or those variables all together on the left side, and then setting the right sides equal to each other so that everything that's the same drops out, disappears, cancels, goodbye. That's the key to this nice little mathematical trick. Some basic kinematics. Now remember, the only thing that's really going to be different on the different planets is the acceleration due to gravity. Now, of course, the differences in acceleration due to gravity will change the amount of time it takes an object to hit the ground falling from a specific height, or it'll change the amount of distance that an object covers while falling a certain amount of time. All right? So now here we have the acceleration due to gravity for the Earth, for the Moon, and for Jupiter. And we're going to do some calculations in just a minute, but before we do the calculations, let's think about how we think those calculations are going to turn out. So, on which celestial body do you think an object will strike the ground in the least amount of time? In other words, it's going to fall the fastest. So, if we take a coin, for example, and drop it from a height, now you could pick any height, but I'm going to pick a height of 6 meters. All right, I mean, you could pick 1 meter, 2 meters, 4 meters, doesn't really matter, but I'm going to pick 6 meters, all right? So we're going to stand at the top of a structure and drop a coin from a height of 6 meters, all right, on the Earth, on the Moon, and on Jupiter. Again, Jupiter is a gas giant, so you got a little bit of leeway here, a little bit of imagination about how the heck we're going to do that, but in any case. So we're going to drop the coin from a height of 6 meters on Earth, okay, bam, all right. Then we're going to drop the same object from a height of 6 meters on the Moon. Now the Moon is not as strong. The Moon does not have as strong a gravitational field as the Earth. So do you think the coin is going to fall faster or slower? The Moon does not pull down as strongly. So what do you think? Is it going to take more time? Bam. All right? Or less time, woo, for the object to fall 6 meters on the Moon? Well, if you're guessing that it's going to take more time because the Moon is not as strong, it's not pulling the coin down with as much force, with as much gravitational force, and therefore the acceleration due to gravity is less, right? It's going to take longer for that coin to fall the same 6 meters on the Moon than it did on the Earth. All right, so if on the Earth it's, and I'm sure that I'm standing on the Earth here, if on the Earth it's like that, then on the Moon maybe it's something like that. The Moon is not as strong. It's going to take longer. On which celestial body will an object take the longest time to strike the ground? All right, so let's put the Moon here. The Moon is going to be the slowest. All right, now, what about Jupiter? Jupiter has a much stronger gravitational field. All right, objects will experience a much faster acceleration due to gravity than on the Earth. All right, so on Jupiter, all right, because Jupiter is going to pull it down much, much faster, on Jupiter it's going to be something like, woo! Maybe even a little faster than that. All right, so on which celestial body will an object strike the ground in the least amount of time? In other words, the fastest. That's going to be Jupiter. These are our predictions. And then, of course, the number for the Earth is somewhere in between. All right, so we're going to do the calculation now in just a minute, but we're predicting that the time for Jupiter will be the smallest, the time for Earth will be in the middle, and the time for the Moon will be the longest time to fall the same 6 meters. So, as promised, a basic kinematics problem on 3 different celestial bodies. How long will it take an object to fall 6 meters from rest to the surface of the Earth, the Moon, and Jupiter? All right, so what are we given? We're given that in each case, the Earth, the Moon, Jupiter, the initial velocity is 0. The object is being dropped from rest. The distance is the same, in each case, 6 meters. The times, we figure, are going to be different because the accelerations due to gravity are, for the Earth, 9.81, for the Moon, 1.62, for Jupiter, 25.9 meters per second squared. We look at what we've been given, and we select this equation. D equals V initial t plus 1/2 AT squared. V initial is 0, so the V initial times t drops out. We're left with D equals 1/2 AT squared. We're trying to solve for time, so we want to get t by itself. We multiply both sides by 2, so the half drops out, and we get 2D equals AT squared. Divide by A on both sides, and we get finally t squared equals 2D over A. Then we take the square root of both sides, right? Take the square root of both sides, and we end up with t equals the square root of 2d over a. That's the equation that we will be using. Okay, so let's plug in. 2d is 6, Earth is 9.81 meters per second squared. Moon, all right, 2 times 6 is the same. A is what's different. You can put on the bottom, you can put A or G. It doesn't really matter if you call this A or G. G is acceleration due to gravity. G is a type of acceleration. So whether you put A or G, we really don't care. All right, the acceleration for the moon is 1.62. Over here for Jupiter, the acceleration is 25.9. Everything else is the same. The times are going to be different. So 2 times 6 is 12 divided by 9.81. All right, 12 divided by 9.81. All right, then take the square root. Now, what most people do is they forget to take the square root. All right, I just screwed up and I squared it instead of taking the square root. 12 divided by 9.81 equals, all right, now take the square root. All right, 1.106 seconds. Yes, all right. 1.106 seconds. All right, for the moon, 12. Now remember, we said we predicted it would take longer, more time for the object to hit the ground on the moon because the moon isn't as strong. It's not pulling the object down as strongly or as quickly. All right, so we're expecting this number to be bigger than 1.106. Let's see if we're right. 12 divided by 1.62 equals, take the square root. Bam. 2.721. 2.721 seconds. And finally here, 12 divided by 25.9. Then take the square root. What people forget to do, they forget to take the square root. All right, now what did I do wrong here? I did something wrong. 12 divided by 25.9 equals, all right, and then take the square root. Yeah, all right, I did something wrong because the first time the answer I got here was like 35, and that's wrong. We said our prediction, see, this is what's great about making a common sense prediction. We predicted initially that it would take the shortest amount of time to hit the ground on Jupiter. So when I got the answer 35 seconds, I'm like, wait a second, what did I do? Let me double check my math. Now I'm getting 0.6806. And that makes sense. 0.6806 seconds. All right, now, of course, we would round all of these answers to 3 significant figures, because that's what we've got here, 3 significant figures. All right, so let's just do that. 0.6806. Okay, so technically, we should round all of these to 3 significant figures. So this one here, the time to hit the ground on Earth, 1.11 seconds, right? I have to round that to 1.11. This rounds for the moon, the time for the moon, 2.72 seconds. And the time for Jupiter, all right, rounds to 0.681 seconds. Okay? And yes, all right, it took the smallest amount of time to hit the ground on Jupiter. Earth was in the middle, and it took the longest time to hit the ground on the moon. All right, so this has been a very, long, fairly long 2 videos go together, 4.5a and 4.5b, all about all the wonderful things that you can do with the universal law of gravitation. Well, actually, there's a lot more wonderful things you can do. If any of you want to go work for NASA, all right, or maybe the European Space Agency or any other, SpaceX, all right, and start sending satellites up and sending people to Mars, this is how you get started. Okay, so just get good at this stuff, and away you go. I'll see you in the next video.